One of the necessary conditions of any real system is the successful interfacing or connecting together of the various components. In a block diagram, an interface is represented by a line between two blocks, indicating that some sort of signal passes between the blocks. If it were only this easy. The fact is, interfacing is sometimes the most difficult task in getting a system operational. After studying this chapter, you should be able to recognize the characteristics of an operational amplifier and describe how they can be used as the basis for different types of useful amplifiers. Design the following types of op-amp circuits to meet specific requirements: a voltage follower, an inverting amplifier, non-inverting amplifier, summing amplifier, and a differential amplifier. You should also be able to understand the operation of the following types of circuits: integrators and differentiators, active filters, and current loop signal transmission. And finally, understand the concepts of the earth ground and ground loops, magnetic and electrostatic shielding, and the importance of a single point ground. There are several different categories of interfacing requirements. One type of interfacing is between analog and digital circuits. Most controllers are digital, whereas many sensors and actuators use analog signals. This means analog to digital or digital to analog converters may be required, as we saw in Series B or Chapter 2. When designing this type of interface, you must consider such things as resolution, the number of bits, analog voltage level, and conversion speed. Another interface problem is matching voltage levels between components. A sensor may put out a 0 to 0.5 volt range, whereas the receiving component may need a signal in the voltage range of 0 to 10 volts. Or a sensor may put out a high impedance signal, which is easily loaded down and needs to be converted to a stronger low impedance signal. Still, another problem is that some sensors are non-linear, which means that the sensor output voltage is not directly proportional to the parameter being measured. Non-linear sensors may require some correction circuitry. Sometimes several sensors must share the same input port of a controller. This requires an electronic switching circuit capable of connecting different analog channels to the same destination. Another requirement may be to add or subtract analog signals. For example, when the feedback signal is subtracted from the set point in an analog controller. Some situations require that there be little or no signal loss between components, even if they are some distance apart. This might seem to be impossible because all wires have resistance. However, the current loop technique virtually eliminates signal attenuation. Another set of interface problems deals with the handling of electrical noise from the outside world. Although some types of interference can be filtered out, it is usually best to try to prevent the noise from entering the system. This is done with proper shielding and grounding. We will deal with these topics in this series. It will not be an exhaustive treatment because whole books are available on each subject, but it will introduce accepted solutions to various problems. So let's get started.